To Num Academy CET Coaching Classes 2020. The chemistry says that more the energy you put into the bond, harder is it to break. Now let us start discussing about the subject chemistry and the topic classification of elements and periodicity in properties of elements. Topic name: classification of elements and periodicity in properties of elements. Chapter 3. There are many periodic laws based on the periodic arrangement of the elements. First law, Mendeleev's periodic law. The properties of the elements are the periodic functions of their atomic masses. Mostly, the English physicist showed that atomic number is more fundamental property of an element than its atomic mass. Therefore, the position of an element in the periodic table depends on its atomic number than its atomic mass. Modern periodic law. The physical and chemical properties of elements are the periodic functions of their atomic numbers. Types of elements. There are 4 types of elements. They are S block elements, P block elements, D block elements, and also F block elements. Modern periodic law. It states that the properties of elements are the periodic functions to their atomic numbers. Second, the periodicity in properties is due to the repetition of similar outer shell electronic configuration at a certain regular intervals. Third one, in modern periodic table, it is based on modern periodic law in which elements are arranged in increasing order of their atomic numbers. Fourth one, in the modern periodic table, the elements are arranged in rows and columns. These rows and columns are known as periods and groups respectively. Fifth one, the table consists of 7 periods and 18 groups. Sixth one, period indicates the value of n, that is principal quantum number for the outermost or valence shell. Seventh one, same number of electrons is present in the outer orbitals, that is similar valence shell electronic configuration. IUPAC nomenclature for elements. Digits, name, abbreviations with their atomic number above 100. Digits 0, name nil, abbreviation N. Digit 1, name un, abbreviation U. Digit 2, name bi, abbreviation B. Digit 3, name tri, abbreviation T. Digit 4, name quad, abbreviation Q. Digit 5, name pent, abbreviation P. Digit 6, name hex, abbreviation H. Digit 7, name sept, abbreviation S. Digit 8, name oct, abbreviation O. Digit 9, name N, abbreviation E. Classification of elements. S block, P block, D block and F block. S block starts with hydrogen, whereas P block starts with helium, D block starts with the scandium, and F block starts with cerium and thorium, that is lanthanides and actinoids. Elements, valence shell electronic configuration, nature and position in modern periodic table. S block elements. Its valence shell electronic configuration is NS1 to 2, that is N is equal to 1 to 7. Nature, they are metals. Position in modern periodic table is first and second group elements. P block elements. The valence shell electronic configuration is NS2, NP1 to 6, that is N is equal to 2 to 7. Nature, they are metalloids and non-metals, but some of them are metals also. Position is groups 13 to 18. D block elements. Valence shell electronic configuration is N-1D 1 to 10, NS1 to 2, that is N is equal to 4 to 7. Nature, metals. Position in modern periodic table is 3 to 12 groups. 3D series starting with scandium with atomic number 21 to zinc with atomic number 30. 4D series Y with atomic number 39 to cadmium with atomic number 48. 5D series with lanthanum with atomic number 57, hafnium with atomic number 72 to mercury with atomic number 80. F block elements. Valence shell electronic configuration is N-2 F 1 to 14, N-1 S2, N-1 P6 N-1D 0 to 1 NS2, that is N is equal to 6 and 7. Nature is radioactive. Position in modern periodic table is group 3. 4F series lanthanides, 14 elements starting from cerium with atomic number 58 to lutetium with atomic number 71. 5F series actinoids, 14 elements with thorium with atomic number 90 to Lw with atomic number 103. Periodicity in atomic properties. First one, atomic radius. Within a given period, atomic radius decreases from left to right. This is due to the effect of increase in nuclear charge while the electrons are added to the same shell. Within a given group, atomic radius increases down the group. This is due to the increase in number of shells. In the first transition series, the atomic size slightly decreased from scandium to manganese because effect of effective nuclear charge is stronger than the shielding effect. The atomic size from iron to nickel remains almost the same because both the effects balance with each other. The atomic size from copper to zinc slightly increase because shielding effect is more than effective nuclear charge due to D10 structure of copper and zinc. Inner transitional elements. As we move along the lanthanide series, there is a decrease in atomic as well as ionic radius. The decrease in size is regular in ions but not so regular in atoms. This is called lanthanide contraction. Atomic size increases from right to left and it decreases from up to low. Ionization potential or ionization energy. Ionization energy increases along the period while decreases down the group. Factors which influence the ionization energy. First one, atomic size. The larger the size of the atom, the smaller is the ionization energy. Second one, effective nuclear charge. The greater the effective charge of the nucleus of an atom, the more difficult it would be to remove an electron from the atom because electrostatic force of attraction between the nucleus and the outermost electron increases. So, greater energy will be required to remove the electron. Third point, penetration effect of orbitals. The order of energy required to remove electron from s, p, d and f orbitals of a shell is s orbital greater than p orbital greater than d orbital greater than f orbitals. Fourth one, shielding or screening effect. Screening effect results in decrease of force of attraction between the nucleus and the outermost electron and lesser energy is required to separate the electron. Thus, the value of ionization potential decreases. Fifth point, stability of half-filled and fully filled orbitals. According to Hund's rule, the stability of half-filled or completely filled degenerate orbitals is comparatively high. So, comparatively more energy is required to separate the electron from such atoms. Successive ionization energies. Elements with their successive ionization energies. Lithium having the ionization energy 1 520.1 and ionization energy 2, its value is 7297. Ionization energy 3 has the value 11,813. Ionization 4 has the value almost more compared to the ionization enthalpy of 3. Carbon with ionization energy 1 with the value 1086.2. Ionization energy 2 value 2352. Ionization energy 3 value 4620. Ionization energy 4 value 6221. Nitrogen with ionization energy 1 value 1402.1. Ionization energy 2 value 2856. Ionization energy 3 value 4577. and ionization energy 4 value 7474. Third, electron affinity. Electron affinity increases along the period while decreases down the groove. The factors affecting the magnitude of electron affinity are stability of half-filled and completely filled orbitals. The stability of half-filled and completely filled degenerated orbitals of a subshell is comparatively more, so it is difficult to add electron in such orbitals and lesser energy is released on addition of electron, hence the electron affinity value will decrease. Electron affinity increases along the period and decreases down the group. Factors affecting the magnitude of electron affinity. Atomic size. In general, electron affinity value decreases with the increasing atomic radius because electrostatic force of attraction decreases between the electron being added and the atomic nucleus due to increase in distance between them. Second one, effective nuclear charge. Electron affinity value of the element increase as the effective nuclear charge on the atomic nucleus increases because electrostatic force of attraction between the electron being added and the nucleus increases. As the electrostatic force of attraction increases, amount of energy released is more. Third one, screening or shielding effect. Electron affinity value of the elements decreases with the increasing shielding or screening effect. The shielding effect between the outer electrons and the nucleus increases as the number of electrons increases in the inner shell. Stability of half-filled and completely filled orbitals. Stability of half-filled and completely filled degenerate orbitals of a subshell is comparatively more, so it is difficult to add electron in such orbitals and lesser energy is released on addition of electron, hence the electron affinity value will decrease. Electron affinities. Kilojoules per mole. Metal plus electron gives rise to metal as an anion plus energy. Fourth one, electronegativity. Electronegativity of elements increases along the period while decreases down the group. Electronegativity scales. Some arbitrary scales for the quantitative measurement of electronegativities are as under. First one, Pauling scale. If Xa and Xb are the electronegativities of atoms A and B respectively, then 0.208 into root of delta AB is equal to Xa minus Xb if Xa is greater than Xb, or delta AB is equal to 23.06 into Xa minus Xb whole square. Delta AB is equal to EAB experimental minus EAB theoretical, where EAB is the energy of AB bond. In a purely covalent molecule AB, the experimental and theoretical values of bond energy AB are equal. So, delta AB is equal to 0, or 0 is equal to 23.06 into Xa minus Xb whole square, or Xa is equal to Xb. In an ionic molecule AB, EAB experimental is more than EAB theoretical. Pauling assumed the electronegativity value of fluorine to be 4 and calculated the electronegativity values of other elements from this value. Second one, Mulliken's electronegativity. Electronegativity is equal to electron affinity minus ionization potential divided by 2 when both are expressed in electron volt. Third one, Alfred Rocho's electronegativity. If the distance between the circumference of outermost shell and the nucleus is r and the effective nuclear charge Z effective, then Z effective into E square by R square is equal to 0.359 into Z effective divided by R square plus 0.744. Z effective is equal to Z minus sigma, whereas Z is equal to the actual charge present on the nucleus, that is number of protons. Sigma is equal to shielding constant. Factors affecting the magnitude of electronegativity. Atomic radius. As the atomic radius of the element increases, the electronegativity value decreases. Second one, effective nuclear charge. The electronegativity value increases as the effective nuclear charge on the atomic nucleus increases. Third one, oxidation state of the atom. The electronegativity value increases as the oxidation state of the atom increases. Oxidation state means that the number of positive charge. Hybridization state of an atom in a molecule. If the S character in the hybridization state of the atom increases, electronegativity also increases. Hybridization states S character and electronegativity. In hybridization state called sp3, S character is 25% and electronegativity is 2.48. In sp2 hybridized state, S character is 33.33% and electronegativity is 2.75. In sp hybridization states, S character is 50% and electronegativity is 3.25. Fifth one, valency. It is the number of univalent atoms which can combine with an atom of the given element. Valency is given by the number of electrons in outermost shell. If the number of valency of electrons is less than or equal to 4, then valency is equal to number of valence electrons. If the number of valence electrons is greater than 4, then valency is equal to 8 minus number of valence electrons. Many elements exhibit variable valence, particularly transition elements and actinoids. Variation in a period increases from 1 to 4 and then decreases from 4 to 0 on moving from left to right. Variation in a group. No change in the valency of elements on moving down a group. All elements belonging to a particular group exhibit same valency. Metallic character of an element. Non-metallic elements have strong tendency to gain electrons. Non-metallic character is directly related to electronegativity and metallic character is inversely related to electronegativity. Across a period, electronegativity increases. Hence, non-metallic character also increases and metallic character decreases. Down a group, electronegativity decreases, hence non-metallic character decreases and metallic character increases. Ionization energy increases from left to right and electron affinity also increases from left to right, whereas atomic radius decreases down the group, electron affinity increases along the group and ionization energy increases down the group. Atomic radius increases from right to left. Let us discuss some of the questions about this lesson. First question, find the successive elements of the periodic table with ionization energies 2372, 520 and 890 kilojoules per mole respectively. Option A, lithium, beryllium, boron. Option B, hydrogen, helium, lithium. Option C, boron, carbon, nitrogen. Option D, helium, lithium, beryllium. And the answer is option D, helium, lithium and beryllium. Second question, in the modern periodic table, the number of period of the element is the same as option A, principal quantum number, option B, atomic number, option C, azimuthal quantum number, option D, atomic mass. And the answer is option A, principal quantum number. The correct order for the size of I plus, I minus is option A, I greater than, I minus greater than, I plus. Option B, I greater than, I plus greater than, I minus. Option C, I minus greater than, I greater than, I plus. Option D, I plus greater than, I minus greater than, I. And the answer is option C, I minus greater than, I greater than, I plus. For the same value of n, the penetration power of orbital follows the order. Option A, S is equal to P is equal to D is equal to F. and option B, P greater than S greater than D greater than F. Option C, F less than D less than P less than S. Option D, S less than P less than D less than F. And the answer is option C, F less than D less than P less than S. Fifth one, which of the reactions will need the maximum amount of energy? Option A, Na gives rise to Na plus electron. Option B, Ca plus gives rise to Ca plus electron. Option C, K plus gives rise to K plus electron. Option D, C2 plus gives rise to C3 plus electron. And the answer is option C, K plus gives rise to K plus electron. And the solution for this is, as K plus having the electron as 20, as 18, and it is having the stable noble gas configuration, then removing another electron from the stable electronic configuration is very difficult, and it requires a maximum amount of energy. As this question does not give the answer as option A, because sodium having the electrons is equal to 11. By removing one electron, it will attain a stable electronic configuration of a noble gas, that is with electrons 10. So it requires minimum amount of energy, and it will be a stable molecule. Ca plus contains the electrons as 19, and if we remove another electron, it will be attaining a stable noble gas electronic configuration, and so it will require a minimum amount of energy. Whereas option D, carbon 2 plus, will be having electrons as 4. Removing another one does not affect to the stability of the carbon molecule, so it will also require minimum amount of energy. But for the option C, that is removing an electron from the stable electronic configuration of a noble gas, is highly impossible and very much difficult, requiring a maximum larger amount of energy. Sixth one, which of the following statements is incorrect? Option A, ionization enthalpy of 1 of oxygen is lower than that of nitrogen, but ionization energy of 2 of oxygen is higher than that of nitrogen. Option B, the enthalpy of nitrogen to gain an electron is almost 0, but of P is 74.3 kilojoules per mole. Option C, isoelectronic ions belong to the same period. Option D, the covalent radius of iodine is less than its van der Waals radius. The answer is option C. Isoelectronic ions does not belong to the same period. It will be in different periods. Seventh question. The correct order of electronegativity is option A, chlorine greater than, fluorine greater than, oxygen greater than, bromine. Option B, fluorine greater than, oxygen greater than, chlorine greater than, bromine. Option C, fluorine greater than, chlorine greater than, bromine greater than, oxygen. Option D, oxygen greater than, fluorine greater than, chlorine greater than, bromine. And the answer is option B, fluorine greater than, oxygen greater than, chlorine greater than, bromine. Fluorine having the electronegativity of 4 by the Pauli's scaling. Eighth one. Two different beakers contain M1OH and M2OH solutions separately. Find the nature of the two solutions if the electronegativity of M1 is equal to 3.4, M2 is equal to 1.2, oxygen is equal to 3.5, hydrogen is equal to 2.1. Option A, acidic and acidic. Option B, basic and acidic. Option C, basic and basic. Option D, acidic and basic. The answer is option D, acidic and basic. And the solution for the question is, as metal 1 having electronegativity almost equal to the oxygen, so as in solution, to break M1OH bond, it is very difficult. So as hydrogen having the electronegativity less than the metal 1, the H will be released easier, and H released as proton, and so the M1OH beaker is containing the nature of the solution as acidic, whereas M2, its electronegativity is less than the oxygen. So, to break M2OH bond, it is very easier. In the solution, the OH will be released as OH minus, and this solution is a basic solution. The beaker containing M2OH solution, its nature is basic. So, option D, acidic and basic. Ninth question, which one is the strongest acid? Option A, magnesium oxide, option B, calcium oxide, option C, aluminium oxide, option D, sodium oxide. And the answer is option C, aluminium oxide. The solution is, in the magnesium oxide, the oxidation state of magnesium is +2. In the calcium oxide, the oxidation state of calcium is +2. In aluminium oxide, the oxidation state of aluminium is +3, whereas in sodium oxide, the oxidation state of sodium is +1. Higher the oxidation state, more is the acidic strength and more stronger is the acid. So, as aluminium having +3 oxidation state, which is higher than the given options, it is the strongest acid. 10th one, which one will have the highest second ionization energy? Option A, 1s2, 2s2, 2p6, 3s1. Option B, 1s2, 2s2, 2p4. Option C, 1s2, 2s2, 2p6. Option D, 1s2, 2s2, 2p6 and 3s2. And the answer is option A, 1s2, 2s2, 2p6, 3s1. Because 1s2, 2s2, 2p6, 3s1, it is sodium atom, and its first ionization enthalpy will result in electronic configuration 1s2, 2s2, 2p6. It is a stable electronic configuration of a noble gas. So, first ionization enthalpy value will be less. After attaining a stable noble gas electronic configuration, to remove an electron from its orbital is very much difficult, and it requires a very huge amount of energy. So, second ionization energy of this electronic configuration will be very high. In the option B, 1s2, 2s2, 2p4, first ionization enthalpy will result in the electronic configuration 1s2, 2s2, 2p3, and the second ionization enthalpy will result in the electronic configuration 1s2, 2s2, 2p2. This will not affect the stable noble gas electronic configuration, that is 1s2, so it requires lower amount of energy for removing 2 electrons from the given electronic configuration. Option C, 1s2, 2s2, 2p6. This electronic configuration is the stable noble gas electronic configuration, that is neon. So, to remove only one electron, it is so much very difficult and requires a very huge amount of energies. So, its first ionization energy is very high. Then second ionization energy will be very huge and might be it is not possible also. Option D, 1s2, 2s2, 2p6, 3s2. Its first ionization enthalpy will result in the electronic configuration 1s2, 2s2, 2p6, 3s1. It requires a less amount of energy, and it will result in a little stable electronic configuration. But its second ionization energy is also low, and it results in the electronic configuration 1s2, 2s2, 2p6, and it is the very stable noble gas electronic configuration. It will require very low amount of energy. So, the answer is 1s2, 2s2, 2p6, 3s1. It requires highest second ionization energy. Thank you for watching.